The universe begins in silence. A silence vast enough to cradle every star, every world, every dream yet unformed. Across this black canvas, pinpricks of fire shimmer galaxies, suspended like lanterns in an infinite cathedral. For millennia, humanity has lifted its gaze toward this darkness, building observatories of stone, then of glass, then of steel and orbiting mirrors. Each new instrument has pushed sight deeper into time, peeling back layers of the cosmos as though the universe were a manuscript written in light. But with each advance, a sobering truth has emerged. Vision has a horizon. Beyond a certain distance, no telescope can follow. The night sky does not fade because it ends, but because light itself cannot cross the gulf. What reaches us is finite, bounded, and behind that boundary lies an eternal absence. Astronomers know this boundary well. It is painted across the heavens as the cosmic microwave backgrounder relic glow, the afterimage of the Big Bang. It is both a window and a wall. Through it, we glimpse the newborn universe, a fireball just 380,000 years after its birth. Beyond it, nothing can be seen. Photons there are trapped in a fog of primal matter, forever hidden from our eyes. This is the last horizon of sight, the final observatory before the dark, a boundary not of technology, but of nature itself. And here the paradox unfolds. The universe reveals its own beginning, yet conceals what came before. Was there a silence before the fire? A field of inflation stretching space into being, a multiverse flickering beyond reach. At this edge of vision, science confronts its most profound question: when light ends, what remains? From the earliest days of human thought, time itself was measured by the sky. Long before telescopes, before mathematics and equations, there were only naked eyes, tilted upward toward the motion of stars. The first observatories were not towers of glass and steel, but circles of stone. At Stonehenge, the rising of the solstice sun aligned with carved gates. In Babylon, scribes etched the wandering of planets into clay tablets, tracing rhythms across generations. To watch the sky was to watch time itself unfold. Humanity's first calendars were built not from clocks, but from constellations. The stars were memory fixed against the slow drifting of seasons. The moon's cycle carved months into the year, while eclipses carried omens of unseen order. Even then, in an age without telescopes, the heavens revealed both pattern and mystery. Something vast lay beyond, waiting for sharper eyes. In 1609, a Florentine mathematician lifted a tube of glass toward the sky. Galileo Galilei, armed with a crude telescope, transformed the cosmos into a landscape. The moon was no smooth lantern, but a world of shadows and craters. Jupiter was a miniature system, its moons circling in nightly procession. The stars, once thought finite, multiplied into uncountable hosts. Galileo's telescope was more than an instrument, it was the first step toward building observatories, windows through which the universe could be seen not as myth, but as measurable truth. The 17th century birthed not only telescopes, but the mathematics to interpret them. Isaac Newton, reflecting on falling apples and orbiting moons, carved the cosmos into law. Gravity was not divine whim, but a universal force, precise and predictable. Kepler's orbits could be written in ellipses, planets moving with clockwork certainty. Newton's Principia declared the universe a grand machine, every motion a line of geometry. For the first time, humanity believed the entire sky could be mapped, predicted, and mastered. The Enlightenment carried this vision forward. In 1789, William Herschel, with mirrors forged in polished metal, constructed the largest telescope of his age. He swept the heavens, night after night, cataloguing nebulae faint, smudges of light scattered beyond the Milky Way. His star maps revealed that the universe was not a flat dome but a deep ocean, stretching outward in layers upon layers of brilliance. The cosmos was no longer infinite, myth had structure, depth, and boundaries waiting to be charted. Yet, as telescopes reached further, the boundaries only receded. The universe unfolded like an endless corridor. The early 20th century brought a revolution. In the 1920s, at Mount Wilson Observatory, Edwin Hubble pointed the Hooker telescope toward faint spirals of light. What appeared as cloudy nebulae resolved into galaxies, vast cities of stars, each like the Milky Way. The universe was no longer a single island, but an archipelago of billions. Hubble went further still, measuring the redshift of galaxies. They were not still but receding. The deeper he looked, the faster they fled. Space itself was stretching, carrying galaxies away. The universe, once imagined eternal and static, was revealed as dynamic, expanding, alive with motion. Time itself had a beginning. The equations traced back not to infinity, but to a singular moment, a fiery birth, now called the Big Bang. And yet, if the cosmos had a beginning, what evidence of it remained? The answer came by accident, whispered as static across a radio antenna in 1965. Arno Penzias and Robert Wilson, engineers at Bell Labs, were calibrating a microwave receiver when they encountered a faint, persistent hiss. They cleaned the equipment, even evicted pigeons nesting in the horn of the antenna. Yet the noise persisted, uniform in every direction. Unknown to them, Robert Dick and his team at Princeton were preparing to search for precisely such a signal. The afterglow of the Big Bang dot. What Penzias and Wilson had stumbled upon was the oldest light in the universe. The cosmic microwave background, a relic from when the cosmos was just 380,000 years old. In that epoch, the universe had cooled enough for electrons and protons to combine into neutral atoms. Before that moment, light could not travel freely, scattered endlessly by charged particles in a cosmic fog. But as atoms formed, the fog cleared, and photons streamed outward, carrying with them the first true image of the universe. This light, stretched by billions of years of expansion, now glows not as fire but as faint microwaves, filling the sky in every direction. It is the ultimate horizon, the farthest light that can ever be seen. Beyond it lies a walnut of matter, but of opacity. Before the cosmic microwave background, the universe was blind to itself, and so too are we. The discovery of the CM was a turning point. For the first time, humanity could observe not just galaxies and stars, but the infant universe itself. Satellite missions would sharpen this image. COBE in the 1990s, WMAP in the early 2000s, and the Planck satellite in 2009. Each refined the picture, revealing subtle fluctuations, tiny temperature differences, ripples frozen into the fabric of the sky. These ripples were the fingerprints of quantum fluctuations, stretched across space by cosmic inflation. They were, in a sense, the first marks of a primordial clockbeats of physics older than stars. Yet with each new observatory, a profound truth became clear. There is a final boundary. Beyond the cosmic microwave background, no light can ever pass. Telescopes may grow larger, detectors more sensitive, but the wall remains. The universe has drawn its own curtain. From Galileo's lens to Hubble's telescope, from Herschel's star maps to the Planck satellite, each step expanded vision outward. But every new horizon only carried humanity closer to a limit, the edge of what can be known by sight. The cosmic microwave background is both triumph and tragedy, the greatest image science has ever captured, and the last it ever can. It is here, at this horizon, that the idea of the last observatory before the dark takes form. The story of astronomy is not just progress, but confrontation. Each new observatory expands the map, but also clarifies the border. Humanity has learned the age of the universe, 13.8 billion years, and mapped its structure across cosmic scales. But in doing so, it has discovered a final veil, a horizon beyond which no light, no telescope, no equation can carry us. The figures of history mark this journey. Galileo raising his glass tube to the heavens, Newton carving gravity into law, Herschel sweeping the sky for nebulae, Hubble measuring galaxies in retreat, Penzias and Wilson puzzled by the hiss of ancient fire, George Smoot and John Mather painting the CMB with Kobe, and the Planck team tracing the earliest ripples of creation. Together, they revealed not only the cosmos, but its ultimate silence. The last observatory is not a single building, not a telescope on a mountain or in orbit. It is the final horizon etched into the universe itself. The cosmic microwave background is both a gift and a warning. The universe offers its childhood image, but denies its infancy. Before this glow lies the darker region forever hidden, a silence beyond science's reach. Here, discovery meets its own edge, and with it comes the unsettling realization: humanity may never know what lies before the first light. The last observatory does not open onto infinity, it opens onto mystery. For centuries, the universe was thought eternal. The stars burned in silence, and the sky was a fixed dome. Yet by the middle of the 20th century, astronomy revealed a truth far stranger and far more unsettling. The night sky was not was finite in age. Galaxies were not fixed, they were receding, carried away by expanding space. And beyond a certain horizon, light itself could never reach us. The first shock came with the cosmic microwave background, discovered in the quiet hiss of a radio antenna. What appeared as meaningless noise was, in fact, the universe speaking. Across nearly 14 billion years, it was proof that the cosmos had a beginning, that time itself had an origin. But hidden in that discovery was something far more profound, a boundary. The CMB revealed a paradox. It was the most ancient light the universe could ever reveal, but it was also a wall. Beyond it, there was no transparency, no starlight, no photon that could ever reach us. Before 380,000 years after the Big Bang, the cosmos was opaque, a dense fog of plasma. Telescopes, no matter how advanced, could never pierce this veil. The shock was not technologically, was fundamental. The universe had imposed a limit on vision itself. Humanity, for all its ingenuity, had reached a cosmic horizon. The idea of horizons in physics deepened the unease. In the 1970s, Stephen Hawking and others extended Einstein's theory of relativity to its logical edge. Just as a black hole's event horizon traps light forever, the universe itself has an event horizon, a boundary created by expansion. Galaxies receding beyond this limit are lost forever, their light stretched into invisibility. What lies beyond can never be observed, even in principle. The realization was staggering. The observable universe was not the universe itself. It was only the part accessible to us, the part bounded by light's long journey. Beyond it, space continues, perhaps infinitely. But to human eyes, it is erased. And then came the second shock. In 1998, astronomers studying distant supernova discovered that the universe's expansion was not slowing down, as gravity should demand. It was accelerating. Something vast was pushing galaxies apart faster and faster. They named it dark energy. With this revelation, the cosmic horizon became not only fixed, but shrinking in reach. Each year, more galaxies slip beyond visibility. Regions once observable fade irretrievably into darkness. In a distant future, the sky will no longer reveal a cosmos of countless galaxies. It will collapse into emptiness, leaving only the glow of our own stars. The implication is stark. Astronomy itself has a deadline. We live in a privileged age, a narrow window when the universe still reveals its origin and structure. Billions of years from now, no evidence of the Big Bang will remain. The cosmic microwave background will stretch into invisibility. Galaxies will vanish from sight, and cosmology as we know it will be impossible. Future civilizations, if they arise, may believe the universe is static, eternal, and empty just as humanity once did. The horizon of knowledge is not only spatial but temporal. It is closing with time. This recognition rippled through the scientific community. The last observatory is not a metaphor, it is literal. A point will come when the universe conceals its history entirely. The cosmos is not only vast, it is secretive, hiding its earliest chapters behind a veil, and erasing its later ones with relentless acceleration. Stephen Hawking spoke often of horizons. To him, they represented not emptiness, but paradox. Black holes should radiate, evaporating slowly through what is now called Hawking radiation. Yet that idea produced a puzzle, the information paradox. If black holes evaporate, what happens to the information they consume? Does it vanish? Does it survive, encoded somehow on the horizon? The same question echoes across cosmology. If regions of the universe recede beyond our horizon, does their information vanish from the cosmic record, or does it remain hidden but preserved? If the observable universe is only a fragment, what does that mean for the whole? The shock, then, is not only that the universe has boundaries, but that the very laws of physics may break down at them. Einstein's relativity cannot answer what lies before the CMB, or beyond the cosmic horizon. Quantum mechanics, too, falters. At singularities, in black holes, or at the origin of the Big Bang equations, collapse into infinities. Mathematics itself dissolves. It is as if the universe were whispering, this far and no further. The analogy is ancient. Sailors once believed the oceans had edges where ships might fall into void. Telescopes, equations, satellites, these are the ships of modern science. And now, they too have found the edge. For scientists, the recognition was both humbling and terrifying. The universe is not infinitely knowable. There exist questions that cannot be answered, not because tools are lacking, but because reality withholds them. And yet, this very shock carried within it a revelation. The boundaries are not arbitrary. They are precise, measurable, written into the physics of space-time. The age of the universe 13.8 billion years. The distance to the horizon about 46 billion light-years. The thickness of the cosmic microwave background frozen at 380,000 years after the Big Bang. These are not vague mysteries, but sharp ones etched into numbers and maps. But the emotional weight remains. The last observatory is not a mountain peak or a spacecraft. It is the recognition that there is a final sky, that beyond the faint microwave glow, there is darkness, not empty, but unreachable. The shock lies in contrast. For centuries, science expanded horizons without limits. Galileo revealed the moon, Herschel revealed galaxies, Hubble revealed expansion. Each step suggested there would always be more to see, more to uncover. But the cosmic microwave background revealed not only the origin of light, it revealed the end of vision. Even now, astronomers wrestle with this paradox. The CMB shows the infant universe, yet nothing before. Inflation, the rapid expansion that preceded it, remains invisible. The physics of the Big Bang itself, its first moments, its deepest cause, lies forever hidden. The veil is absolute, and so, in the quiet of observatories, under the vastness of night, a profound humility grows. Humanity has touched the edges of knowledge and found them not infinite, but finite. The cosmos is both generous and withholding. It grants glimpses of its origin, yet conceals its birth. It reveals its structure, yet erases it with acceleration. The last observatory is the moment when science confronts this truth, that beyond the glow of the microwave sky, there is no more light to catch, no more galaxies to map. The universe itself withdraws from view. This realization is not an end, but a threshold. For just as horizons in physics conceal, they also suggest. The very limits of knowledge point toward deeper theories, toward quantum gravity, inflation, multiverses and realities beyond our own. The shock of the horizon is also the spark of speculation. But at its core, the discovery remains unsettling. The cosmos, once thought infinite and open, is instead bounded by silence. The final frontier is not space itself, but the limits of what can be seen, known, or proven. Here, at the horizon of knowledge, astronomy becomes philosophy. The last observatory stands as a reminder. Science may map the stars, but it cannot map the void beyond them, and perhaps it was never meant to. If the cosmic microwave background was the wall, then science's task became not to pass through it, but to study its every ripple. The shock of discovery soon gave way to a new era of precision, an attempt to read in faint light the hidden story of creation. The first great tool was COBE, the Cosmic Background Explorer. Launched in 1989, for the first time, humanity saw the sky at wavelengths invisible to the eye, stripped of atmosphere and distortion. COBE confirmed what theory had long predicted. The cosmic microwave background followed a perfect black-body spectrum, the signature of a hot, dense origin. The universe, once a seething fireball, had cooled into a whisper of microwaves. But within that whisper, COBE also found something else tiny, fluctuations in temperature, 1 part in 100,000. These were not noise, but structure. The seeds of galaxies, written in the sky itself. George Smoot, who led the mission, compared it to seeing the face of God. The remark was poetic, but the science was no less profound. The universe had revealed not only its birth, but its blueprint. From COBE, the trail passed to WMAP. Launched in 2001, with sharper eyes, WMAP mapped the anisotropies of the microwave sky across the whole celestial sphere. The patterns were not random. They showed the fingerprints of sound acoustic oscillations in the primordial plasma, waves frozen into light. These baryon acoustic oscillations were the fossils of cosmic rhythm, vibrations of matter and energy from when the universe was only 380,000 years old. The Planck satellite, launched in 2009, carried this quest to its peak, with exquisite resolution. It mapped the microwave sky to its limits, producing a portrait of the early universe that rivaled any painting in its subtlety. From Planck's data came precise numbers. The age of the universe at 13.8 billion years. The density of matter and energy, the ratio of ordinary matter to dark matter, and the faint hints of cosmic inflation, a process that stretched the newborn universe faster than light. But with clarity came new mystery. The CMB was not perfectly uniform. It carried anomalies, a large-scale asymmetry, a cold spot, strange alignments that seemed to defy randomness. Some called it the axis of evil, an ominous name for patterns that hinted at deeper physics. Perhaps even influences from before the observable universe. The CMB was not the only fossil. In the distribution of galaxies, scientists found echoes of those same primordial sound waves, baryon acoustic oscillations imprinted into cosmic structure. By mapping millions of galaxies, surveys revealed how the early universe's vibrations became the scaffolding of cosmic web, the vast network of filaments and voids stretching across billions of light-years. Yet photons were not the only messengers. Neutrinos, ghostly particles born in nuclear reactions, forged another path. They had streamed freely from the first second after the Big Bang, long before light could travel. Detecting them became an obsession. In Antarctica, the Ice Cube Observatory carved into ice, and in Japan, Super Kamio Konde's underground chamber. Physicists searched for neutrinos that carried whispers from the earliest universe. Each particle that passed through these detectors was a relic older than starlight, older even than the microwave sky. And then there were gravitational waves. Predicted by Einstein, confirmed a century later by LIGO. They offered a new kind of observatory, one that did not rely on light at all. Ripples in space-time itself could, in principle, carry information from the first instant of creation. If detected, primordial gravitational waves would bypass the wall of the CMB, reaching into epochs where photons could not go. Experiments. From LIGO to the planned LISA mission seek this signal, straining to hear the faint tremor of inflation imprinted on space-time itself. The deeper science reached, the more it confronted limits. Inflationary models predicted subtle non-Gaussian patterns in the microwave background. Faint signatures of quantum fluctuations stretched to cosmic size. Planck searched, but the evidence remained elusive. Neutrino experiments struggled with the sheer difficulty of detecting particles that ignored matter almost entirely. Gravitational wave detectors, though successful at capturing stellar collisions, had yet to glimpse the primordial background, and yet each effort expanded the last. Observatory. If light had a boundary, other messengers might reach further. Neutrinos, gravitational waves, cosmic rays. Each carried the hope of crossing the horizon in a new way, of finding cracks in the veil. But even here, the silence grew louder. Quantum field theory predicted vacuum fluctuations, an infinite sea of energy even in empty space. These fluctuations may have driven inflation, sculpting the very universe we see. But the same equations led to infinities, numbers so vast they mocked calculation. The cosmological constant problem, why the vacuum energy predicted by quantum theory exceeded observation by 120 orders of magnitude, remained the greatest unsolved puzzle in physics. It was as if mathematics itself had faltered, offering answers. Beyond reason, at particle accelerators, physicists sought clues. The Higgs boson, discovered in 2012, revealed the field that gave particles mass. Yet questions remained. Was the Higgs stable? Could the universe exist in a false vacuum, doomed to collapse? Could inflation itself be tied to the Higgs? These mysteries linked the smallest scales of quantum fields to the largest expanses of cosmology, uniting particle physics and the last observatory in a single question. What happened at the beginning? Supercomputers added their voice. Simulations of cosmic structure, seeded by fluctuations in the microwave background, produced webs of galaxies eerily similar to reality. By adjusting parameters, dark matter density, dark energy, strength, inflationary seeds, scientists tested theories against the cosmic map. Each run was an artificial universe, a mirror to the one we inhabit. Yet no simulation could step beyond the veil. The initial conditions, the true origin, remained hidden. The deeper the investigation, the clearer the paradox became. Science could measure the universe with extraordinary precision, down to fractions of a percent. Yet the most fundamental questions, the nature of inflation, the meaning of dark energy, the cause of anomalies, remained beyond reach. The last observatory was not a point, but a horizon, advancing as instruments improved, but never receding. Entirely still, the search continued. In the cold silence of Antarctica, Ice Cube waits for cosmic neutrinos. In underground caverns, detectors strain to hear the faint collisions of dark matter particles. In Chile's Atacama Desert, telescopes map the polarization of the microwave background, searching for the swirl pattern that inflation should have left behind. In laboratories, physicists cool atoms to near absolute zero, creating analogues of black holes to test the physics of horizons. Each effort is a gesture toward the unseen, a reaching hand into the dark. For scientists, the deeper investigation is not simply technical, it is philosophical. Each discovery confirms that the universe is intelligible, yet each limit reminds us that intelligibility has boundaries. The CMB is a photograph of the infant cosmos, yet the moments before remain shrouded. Gravitational waves may one day reveal inflation, yet the cause of inflation itself may never be known. The last observatory is a paradox of progress. Every advance sharpens vision, yet every advance confirms the inevitability of the veil. Light, neutrinos, gravity all carry messages from creation, but none can speak the whole story. The closer science draws to the beginning, the more it feels the silence beyond. And perhaps this is the truest meaning of the last observatory. Not a single telescope, not a single satellite, but the recognition that all tools, all messengers, all methods converge at the same horizon. The universe opens its book only so far. Beyond that, the pages are blank, waiting for theories, waiting for imagination, but forever beyond observation. The deeper investigation, then, is not only about instruments or data. It is about human persistence, the refusal to stop at the veil. It is about the willingness to measure, to calculate, to search, knowing that the horizon recedes but never disappears. It is about the humility to confront silence and the courage to keep listening. In the quiet chambers of observatories, in the hum of supercomputers, in the frozen depths of Antarctic ice, the investigation continues. Each photon, each neutrino, Each ripple of space-time is a fragment of a cosmic story billions of years old. Together, they form the last great observatory, the final effort before the dark. And still, beyond the veil, mystery waits. The deeper science pressed into the relic light of creation, the stranger the universe appeared. What seemed, at first, like the smooth afterglow of the Big Bang revealed cracks, blemishes, and alignments that defied expectations. The closer the gaze, the more the cosmos seemed to whisper of secrets it did not intend to share. The Planck satellite's precision, though celebrated, carried with it a shadow of unease. The microwave sky was not as statistically innocent as theory had promised. On the larger scales, the distribution of temperature fluctuations carried asymmetries, alignments that pointed in one direction across the heavens. Cosmologists nicknamed it the axis of evil. The phrase was playful, yet it masked a serious tension. If the cosmos was born in inflation, expanding from a random froth of quantum fluctuations, then no preferred direction should exist. Yet, there it was, an alignment written across billions of light years, as if the universe itself possessed an orientation. Another blemish lurked. The cold spot, a patch of sky hundreds of millions of light years across where the microwave background was anomalously cool. Some argued it was merely statistical fluke. Others suggested it could be the fingerprint of something beyond the observable universe, perhaps even a collision with another bubble universe in the inflationary multiverse. If true, then the last observatory was not simply a wall of light, but a scarred frontier hinting at realms unseen. The mystery deepened further in the expansion of the cosmos itself. The discovery of dark energy in 1998 had already overturned centuries of assumption. Rather than slowing under gravity's pull, the expansion of the universe was accelerating. Galaxies were not only receding, they were fleeing faster and faster, carried on a tide no one could explain. And the mathematics carried a grim revelation. There was a horizon, beyond which galaxies recede faster than light, their signals cut off forever. Already, tens of billions of galaxies lie beyond reach, their light erased from the record of the observable universe. Each year, more slip away. The last observatory is not only a spatial boundary, but a temporal one. The universe is actively erasing its past, hiding its own structure from the eyes of future astronomers. Consider the far future. Trillions of years hence, when stars have burned to embers, the accelerating expansion will render every galaxy but our own invisible. The cosmic microwave background will redshift into silence, stretched until it disappears entirely. Future beings, no matter their intelligence, will look into the sky and see only emptiness. The evidence of the Big Bang, the scaffolding of modern cosmology, will be gone. They will never know the universe had a beginning. This realization cuts deep. Humanity exists in a privileged cosmic moment, the narrow window when the universe still reveals its history. We are witnesses to a fleeting transparency, an interval before the sky closes forever. The last observatory is not a metaphor. It is literal. Beyond this epoch, knowledge itself will fade. The anomalies sharpen the paradox. Inflation was proposed to solve the puzzles of the early universe, its smoothness, its flatness, its uniformity. Yet in solving them, inflation opened new abysses. What field drove this exponential expansion? How long did it last? What ended it? The answers remain veiled, and in some models, inflation is eternal. Quantum fluctuations create pockets of space that inflate endlessly, producing an infinite multiverse. Our observable universe would then be one bubble among countless others, separated by horizons forever uncrossable. If this is true, then the last observatory is not only the end of vision, but the end of relevance. Most of the multiverse would be forever hidden, unknowable even in principle. The scars in the CMB, the cold spot, the axis of evil might be the only fingerprints of collisions with other bubbles, the only faint evidence that our cosmos is not alone. But certainty will never come, for by definition, the multiverse lies beyond observability. The mystery deepens still further in the very nature of time. If the observable universe emerged from inflation, what came before? Was there a before? Or did time itself begin at the Big Bang? Roger Penrose has argued that the universe may not be a one-time event, but part of a cycle. In his conformal cyclic cosmology, the remote future of one universe, when all particles have lost their mass and all black holes have evaporated, becomes indistinguishable from the Big Bang of the next. The last observatory, then, may hold subtle circles in the CMB echoes of collisions between black holes from eons before our own universe. Planck data has hinted at such features, though debate continues. Even entropy, the arrow of disorder, complicates the picture. If the universe is younger than its entropy suggests, then some deeper clock must have been ticking before creation. Perhaps the last observatory hides not only a spatial horizon, but a temporal one. Perhaps we see only a single tick of a rhythm, far older than the cosmos itself. Dark energy, too, adds its weight. Its density appears constant, unchanging over billions of years. It acts like a clock, steady, unwavering, driving the acceleration of the universe at a rate that appears timeless. Yet we do not know its nature. Is it a property of the vacuum, a cosmological constant, or a dynamic field evolving slowly, concealing a deeper law? The last observatory hides the answer, for dark energy leaves only its gravitational fingerprints, its true essence veiled. The implications are staggering. If inflation is eternal, then universes are born endlessly beyond our horizon. If Penrose is correct, then our universe is one in an infinite chain of cycles. If dark energy is unstable, the cosmos may one day collapse into a big rip, tearing galaxies, stars, atoms apart. In every case, the last observatory looms the horizon beyond which no data flows, no observation penetrates, and so the escalation is not only scientific, but existential. Cosmology, once a science of confident maps, is now confronted by horizons it cannot cross. The more instruments reveal, the more the darkness asserts itself. The observable universe is vast, yet bounded. The full universe may be infinite, yet forever hidden. This is the crisis and the wonder, to know that we can measure the universe with exquisite precision, yet remain locked within a horizon, imprisoned by the speed of light and the expansion of space. The last observatory is both triumph and tragedy. It gives us the story of creation, but denies us its origin. It offers a glimpse of structure, but hides the whole. Here the philosophical stakes sharpen. If science depends on observation, and observation has a horizon, then is truth itself bounded? Are there realms of reality that can never be known, not because of ignorance, but because of principle? If so, then the last observatory is not a frontier we may one day cross, but a wall built into the fabric of reality. And yet, paradoxically, this wall may be the most meaningful discovery of all, for it tells humanity that the cosmos is not infinite chaos, nor infinite clarity, but something in between. It reveals, then conceals. It allows knowledge, then withholds it. It offers a stage upon which intelligence may arise, seek, and wonder, before drawing its curtain closed. The escalation of mystery is not only about anomalies or dark energy, but about this fundamental drama. The universe is knowable, but only so far. Beyond lies silence. The last observatory is the recognition of this silence, and the courage to look into it. At the edge of observation, when light fades and cosmic maps fall silent, theory becomes the last lantern. The universe may no longer yield photons, but it still yields questions, and questions demand answers, from the void beyond the last observatory. Scientists have drawn some of the most daring visions in all of physics. The first is inflation, proposed in the early 1980s by Alan Guth, later refined by Andre Linde and others. Inflation explains how the universe, born in chaos, became so smooth and flat. A fraction of a second after the Big Bang, space itself may have expanded faster than light, stretching quantum fluctuations into cosmic architecture. The ripples of galaxies, the distribution of matter, the faint scars in the cosmic microwave. Background all may be fossils of inflation's breath, yet inflation is not a single theory, but a family. Some versions end cleanly, producing a single universe like our own. Others, however, are eternal. In these models, inflation never stops. Quantum randomness ensures that while inflation halts in some regions forming bubble universes like ours, it continues endlessly elsewhere. The cosmos becomes a fractal foam, an infinite multiverse. Each bubble may have its own laws of physics, its own constants, its own stars and galaxies. If true, then the anomalies in the CM be the cold spot. The axis of evil might be bruises from collisions with neighboring bubbles. But the irony is cruel. If these other universes exist, they lie forever beyond observation. The last observatory would not only be a frontier, but a prison wall, unbreakable. Roger Penrose offers another speculation. His conformal cyclic cosmology imagines the universe not as a one-time explosion, but as an infinite sequence of eons. In his vision, when the current universe grows old, when black holes evaporate and all mass decays, the cosmos will consist only of radiation. In such a state, time loses its meaning. Without mass, without clocks, the end of one universe becomes indistinguishable from the birth of another. Our Big Bang, in this daring proposal, was the fading heartbeat of a previous cosmos. Penrose has claimed that faint circular imprints in the CMB may already show evidence of these older eons, echoes of black hole collisions predating our creation. Critics remain skeptical, but the allure persists. Perhaps the last observatory hides not nothingness, but the memory of worlds before ours, quantum gravity. The long-sought union of Einstein's relativity and quantum mechanics offers its own possibilities. In loop quantum gravity, space-time is not continuous but granular, woven of tiny loops at the Planck scale. Singularities points of infinite density are, thus smoothed. The Big Bang may not have been a beginning, but a bounce, a transition. From a previous contraction, in this picture, the last observatory conceals not a void, but the rebound of a universe before ours. String theory paints a different picture. In this framework, the fundamental particles of reality are not points, but vibrating strings. Their resonances give rise to quarks, electrons, and photons. But strings require extra-dimension spatial folds hidden from ordinary sight. Singularities may dissolve into smooth geometries within these higher dimensions. Inflation might be driven not by fields, but by the collisions of higher dimensional brains. In this speculation, the last observatory may hide dimensions folded tightly against our own, invisible to light but real nonetheless. There are more radical ideas. Still, the holographic principle, born from the physics of black holes, suggests that space-time itself is not fundamental. The universe we see may be a projection, its true description encoded on a distant surface. In such a framework, the last observatory would not be the end of space, but the edge of a hologram. Beyond it lies not darkness, but the deeper surface, upon which our universe is inscribed. Dark energy, discovered in 1998, has also inspired speculation. If its density is truly constant, it acts like a cosmological constant, a timeless push embedded in the fabric of space-time. But if it evolves, if it is the manifestation of a field called quintessence, then it may change the fate of the cosmos. Some scenarios predict a slow fade, others a catastrophic big rip, in which the acceleration grows without bound, tearing apart galaxies, stars, planets, even atoms. In that endgame, the last observatory would shrink until nothing remained, a cosmic horizon swallowing itself. Other theorists contemplate the possibility of false vacuum decay. Our universe may be trapped in a metastable state, a valley of low energy that is not the lowest possible. If quantum tunneling were to occur, the vacuum could collapse to a true ground state, rewriting the laws of physics in an instant. This cataclysm would expand at the speed of light, unobservable until it arrives. If so, the last observatory hides not only the past, but the possibility of abrupt annihilation. And then there is the multiverse in its purest philosophical form. If the laws of quantum mechanics allow every possible outcome to occur, then every history, every variation of constants, every arrangement of matter may exist somewhere. Our observable universe is merely one branch among infinitely many. In such a landscape, the last observatory is not a barrier but a reminder that our reality is a single chapter in a library without end. These theories share a haunting common thread. They cannot be verified directly. The last observatory is absolute. In its silence, inflation leaves only scars in the CMB, faint and contested. Cyclic universes leave whispers that may or may not exist in the data. String theories, extra dimensions remain beyond detection. The holographic principle is supported mathematically, but awaits decisive experiment. Dark energy remains inscrutable, its essence unknown, and yet speculation is not futility. It is a necessary act of imagination at the edge of knowledge. Einstein once built relativity not on data alone, but on thought experiments: the elevator, the speeding train. Today, theorists build universes in equations, guided by consistency, mathematics, and the fragments of evidence we do hold. Theories are the scaffolding with which humanity peers over the wall of the last observatory, glimpsing possibilities beyond. But speculation also forces philosophy upon science. If universes exist beyond observation, are they science or metaphysics? If the last observatory is absolute, then must knowledge itself have boundaries? Some argue that if a theory explains observable features, like inflation explaining the CMB, retains validity, even if its full implications are unobservable. Others warn that without falsifiability, physics drifts toward myth. Perhaps, then, the deeper truth is that the last observatory is not only cosmic, but cognitive. It is the point where the human mind confronts the limits of its tools, where imagination must reach where light cannot. Beyond this horizon, mathematics stretches, but certainty fades. Theories become bridges built over silence, elegant but untested dot. And yet, this may be the essence of science. For every equation that worked, there was first a moment when it did not. For every discovery, there was first a speculation. At the edge of the last observatory, theories and speculations are not weaknesses, but the seeds of revolutions yet to come. The universe may never yield its deepest truths, but it is, in the attempt stringing together inflation, cycles, holograms, and multiverses, that humanity honors its place, not as masters of the cosmos, but as its witnesses. As the silence deepens, theory becomes our language of hope. At the frontier of the last observatory, speculation alone cannot stand. Theories, however beautiful, demand confrontation with the world. And though the cosmos hides behind its horizon, humanity has built machines of extraordinary ingenuity to press against that veil. These instruments are not mere telescopes or detectors. They are time machines, peering across billions of years. They are translators, converting silence into data, rendering invisible particles into signals on screens. They are the scaffolds upon which our species leans, straining toward truths that light itself refuses to yield. The most familiar are telescopes, yet they are no longer simple tubes of glass. On mountaintops in Chile and Hawaii, on desert plateaus and icy ridges, enormous mirrors gather faint whispers of starlight. The European Southern Observatory's very large telescope, the twin Keck mirrors, and soon, the extremely large telescope with its 39-meter span. These are observatories carved from mountains, designed to collect photons born in the earliest galaxies. Their purpose is to pierce the epoch of reionization, when the first stars burned the fog of hydrogen clear. Each observation brings us closer to the wall of the cosmic microwave background, but never beyond. In orbit, free from the blurring atmosphere, other eyes keep watch. The Hubble Space Telescope has become an icon, delivering images of galaxies at the edge of time. Its successor, the James Webb Space Telescope, now stares deeper still, collecting the infrared glow stretched by cosmic expansion. Webb's mirrors gather light from galaxies less than 300 million years after the Big Bang fossils of the universe's youth, and yet Webb too is bound. Beyond that age, the cosmos remains opaque, photons scattered by primordial plasma. Future missions already stir in the plans of agencies. The Nancy Grace Roman Space Telescope and Europe's Euclid mission aim to map dark energy's influence on the cosmic web. By charting billions of galaxies, their surveys will measure how structure grew and how acceleration changed across time. Dark energy, the mysterious driver of cosmic expansion, is itself a kind of horizon, one whose nature may determine whether the universe fades gently, collapses suddenly, or tears itself apart. These telescopes are built not only to see, but to measure the unknown force that erases sight itself. Beyond light, astronomers now listen to the ripples of space-time. In 2015, LIGO captured the first gravitational waves, tremors from colliding black holes over 1 billion light-years away. Each wave carried not photons, but distortions of reality itself, a trembling of the cosmic fabric. Where light is blocked, gravitational waves may pass unhindered. In this, some physicists glimpse a new observatory, one that may pierce the first moments after the Big Bang. Future detectors expand this frontier. LISA, the Laser Interferometer Space Antenna, will float in space, 3 spacecraft forming a triangle millions of kilometers wide. sensitive to waves with periods of hours. LISA could detect the signature of supermassive black hole mergers, and perhaps even the primordial waves left by inflation. On Earth, pulsar timing arrays networks of millisecond pulsars monitored for tiny irregularities have already hinted at a background of gravitational waves. These may one day reveal the rhythm of the cosmos before photons could escape. Another class of instruments hunts particles so ghostly they pass through entire planets without pause. Neutrino observatories buried deep beneath ice or rock capture flashes of blue Cherenkov light when one of these elusive messengers collides with matter. At the South Pole, IceCube watches a cubic kilometer of Antarctic ice. In Japan, Super Kamiokande and its planned successor, Hyper Kamiokande, use vast caverns filled with pure water. Neutrinos were born in the Big Bang, long before photons decoupled. Detecting them is like touching the fabric of the universe at its most infant stage. A future neutrino observatory may one day detect the cosmic neutrino background, relics from the first second of time, particles that carry memory from beyond the last observatory of light. The search for dark matter adds another suite of tools. Deep underground, detectors wait for faint signals of weakly interacting massive particles, hypothetical constituents of the invisible scaffolding shaping galaxies. Experiments like Xenon 1T in Italy or Lux Zeppelin in the United States attempt to catch the rarest flickers of interaction. On a larger scale, weak gravitational lensing surveys trace dark matter indirectly, watching how it bends light from distant galaxies. Though dark matter cannot be seen, its fingerprints are everywhere. To map it is to map the invisible bones of the cosmos. Meanwhile, particle colliders probe the universe in miniature. At CERN's Large Hadron Collider, protons crash together at near-light speeds, recreating energies similar to those moments after the Big Bang. These collisions allow physicists to test theories of Higgs field stability, search for particles, and explore the possible links between particle physics and cosmology. Future colliders, larger and more powerful, may push even closer to the Planck scale of energy, where quantum gravity reveals itself, and where singularities may dissolve into new physics. Quantum simulators offer another route. In old laboratories, physicists trap atoms in states of near absolute zero, arranging them into lattice that mimic equations of spacetime. Some of these systems produce analogues of black holes, horizons in miniature where Hawking-like radiation may be studied. Though these simulators are not the universe itself, they are models-controlled environments where the rules of reality may be tested at the edge of theory. Supercomputers, too, have become observatories in their own right. By simulating billions of particles of matter and energy, they recreate cosmic evolution. The Illustris and Millennium simulations map the growth of galaxies, tracing filaments of dark matter and rivers of baryons. Other simulations attempt to model inflation, string cosmologies, or cyclic universes, comparing their predictions to the actual distribution of galaxies or the anisotropies of the CMB. Though virtual, these universes offer a testing ground where equations confront observation. Even the measurement of cosmic silence has become an instrument. Radio telescopes like the Square Kilometre Array, under construction in Australia and South Africa, will chart neutral hydrogen from the cosmic dawn. By mapping its distribution, astronomers hope to understand the birth of the first stars and galaxies. Each detection is not just an image, but a data point in the long narrative of structure rising from fluctuation together. These tools form a cathedral of observation, built not of stone but of detectors, mirrors, and algorithms. Each one pushes closer to the wall of the last observatory. Each one gnaws at its silence, but none can break it. The cosmic microwave background remains the final canvas of light. Beyond it lies only speculation. Gravitational waves and neutrinos may pierce further, but they too have limits. The universe, it seems, enforces boundaries on knowledge, and yet the pursuit continues. The Roman telescope readies its instruments, Euclid gathers its maps, CMBs for weights to launch. Lisa takes shape, and colliders dream of new energies. Each machine is humanity's declaration that the cosmos cannot hide without resistance. The last observatory may be final, but science will press against it until its very edge glows with understanding. Perhaps that is the ultimate meaning of these tools. They are not only devices to gather data, they are symbols of persistence, the refusal to let mystery stand unchallenged. They are proof that curiosity, though fragile, can summon machines as vast as mountains and as precise as atoms. They are humanity's attempt to write one last equation on the dark horizon, even knowing it may never be solved. The last observatory cannot be crossed, but with every telescope, every detector, every simulation, humanity moves closer to the veil, mapping it with care. And when the darkness finally closes, when galaxies slip beyond sight and the cosmic background fades, the record of these tools will remain a chronicle of how far we reached and how fiercely we tried. The last observatory is not a place one can visit. It has no walls, no dome, no instruments perched upon its roof. It exists at the edge of knowledge itself, where observation falters and the cosmos withholds its deeper truths. Humanity has spent millennia building steps toward its stone circles aligned to solstices, telescopes of bronze and glass, arrays of mirrors larger than cathedrals, detectors carved into the earth itself. Each has carried sight further. Each has peeled back another layer of night. And yet, at the end, all discoveries converge on the same realization. There is a limit. There is a veil that no machine can pierce. It is a strange fate for a species defined by curiosity. To know that the universe is vast, to know that there is more beyond the horizon, and yet to accept that it may forever remain hidden. The paradox is almost unbearable. For centuries, humans believed ignorance was temporary, that every question, however profound, could be answered with better tools, sharper equations, or more refined observations. But the last observatory whispers something different. It whispers that truth itself may come with boundaries, and that some mysteries are woven not for solution, but for contemplation. Yet in that boundary lies beauty. The cosmic microwave background, the horizon of light, is both wall and revelation. It shows us the universe as a child of only 380,000 years. It carries the frozen fingerprints of the first atoms, the whisper of inflation, the possibility of universes before our own. It is not a blank refusal, but a gifter, final message carried across nearly 14 billion years of time. And perhaps that is enough. Perhaps the act of receiving that message, of deciphering its delicate fluctuations, is itself an encounter with the infinite. The last observatory also reshapes what it means to be human. For all of recorded history, people measured themselves against the cosmos. Ancient myths imagined heavens as eternal, fixed, unmoving. Later, Copernicus dethroned Earth from the center. Newton revealed universal law. Einstein bent space and time into geometry. Each shift humbled humanity, but each also elevated it, for to comprehend the vastness is to transcend smallness. Standing at the boundary of sight, humanity is once again humbled, yet this time the humility is sharper. Not only are we not central, we may not even be capable of knowing the full story. This is not merely a scientific recognition. It is a philosophical revolution. If the universe hides its earliest moments behind silence, then truth may not be absolute but contextual. The Big Bang may not be the beginning, but only the beginning of our knowledge. Beyond could lie cycles of universes, or infinite multiverses, or realities so alien that language cannot touch them. But they remain beyond reach, beyond even imagination. To live with that unresolvable gap is to live with mystery not as obstacle, but as companion. This, the last observatory, becomes a mirror. It reflects not just the cosmos, but humanity itself, strengths, its frailties, its longing. The instruments that probe the sky are built not out of necessity, but out of yearning. They are monuments to wonder, testaments that a species can find. To a single planet dared to look across billions of light years. Whether the horizon yields all its secrets or none, the act of looking transforms the looker. Perhaps, too, the last observatory reminds us of time. The horizon is not fixed, but shifting. Already, galaxies beyond 16 billion light-years recede faster than light, lost forever to vision. The cosmic microwave background itself will fade, its photons stretched into oblivion by expansion. Trillions of years hence, no observatory, no matter how powerful, will see evidence of a Big Bang. The future universe will appear dark and static, its history erased. Humanity lives in a fleeting moment, a cosmic dawn when the sky still tells its story. To know this is to feel urgency, a responsibility to preserve the record, to write down the sky before it disappears. And yet, there is solace. For even as the physical horizon closes, the horizon of imagination expands. Equations falter, telescopes reach their limit, but thought remains unbounded. If the multiverse is unreachable, it can still be conceived. If pre-Big Bang states are unknowable, they can still be modeled, speculated, dreamed. Imagination itself becomes the last instrument, extending beyond photons and waves into the realm of philosophy and myth. In this way, the last observatory is not an end, but a beginning. There is also a deeper symmetry. Ancient humans looked upward with naked eyes and saw a mystery they could not resolve. They told stories of gods, of eternal fires, of wheels of time. Today, with instruments more powerful than their wildest visions, humanity peers to the edge of creation and finds another mystery, more profound, more precise, but no less humbling. The circle closes. Knowledge expands, but mystery does not vanish, it only deepens. Perhaps this is the true nature of science, not the conquest of mystery, but its cultivation. To replace shallow questions with profound ones, to transform ignorance into awe. The last observatory does not end science. It gives it purpose. It reminds us that the act of seeking is as vital as the act of finding, that discovery is not a destination, but a journey whose horizon forever recedes. What then does it mean for humanity? To stand on this small planet, around a common star, in a galaxy of billions, gazing at the last light of the universe's dawn. It means fragility, yes, but also resilience. It means that in a cosmos of unimaginable scale, a creature of fragile flesh dared to ask questions that even the universe itself resists answering. It means that meaning is not handed down from the stars, but created in the asking. The last observatory is not defeat. It is the clearest reminder of what it means to be alive in a thinking universe. It is proof that knowledge is not infinite, but wonder is. That the dark beyond sight is not emptiness, but potential and invitation to imagine. And so the story ends where it began, in silence. The sky stretches into blackness, galaxies thinning into void, until only the afterglow of the Big Bang remains. Beyond, nothing can be seen. Yet, in that darkness lies a reflection, not of what is hidden, but of what is revealed. The last observatory stands not on mountain tops, nor in orbit, nor carved into ice. It stands within the human spirit, the unyielding flame of curiosity. It is the willingness to ask, even when no answer is given. The universe conceals itself. The horizon closes. The dark approaches. But as long as there are eyes to look, as long as there are minds to wonder, the last observatory endures, not as a machine, not as a boundary, but as a truth, that to seek is to be human and to live. In mystery is to live in meaning.